What's happening, everyone? In this video I'll be taking a closer look at the binary search tree data structure using the Python coding language, specifically Python 2.7. Same as the prior videos in this series. In the beginning of this video we'll cover some of the basics of the binary search tree, and later on we'll open up a coding editor and implement the data structure itself, along with any functions and algorithms we'll need to operate it properly. As always, if you find the video useful, be sure to throw me a thumbs up. Also, consider subscribing to the channel if you'd like to stay current on my coding and virtual reality content. If you have any suggestions on certain data structures or algorithms to cover in future videos, or just want to say anything in general, don't hesitate to post a comment. I'll certainly read through them all and answer any questions you may have. So to start off with, a binary search tree is simply another way to store data, similar to a linked list, which we've also covered in a separate video in this series. A binary search tree is essentially a set of nodes. If you recall, in a linked list we enforce certain node protocols. For example, we only allow a single connection to leave each node, and we can either allow or prevent nodes from having connections back to their parents. We also enforce higher level protocols whose jobs are not to manage specific nodes but to manage multiple nodes at a time. For example, we may disallow our linked list from having any loops. This idea of the actual information being contained in the organization of the nodes rather than the nodes themselves is a prevalent idea as we make our way over to the binary search tree. First of all, to understand the cumbersome naming, a binary search tree is simply a specific type of binary tree, which itself is just a specific type of tree. The binary in binary tree means we can, at most, have two connections leaving each node. From now on, we'll call the nodes below a node its children. The search in binary search tree alludes to one of those higher level protocols we were talking about earlier. We'll cover it in more depth later, but essentially, assuming we're using integer values for each node, every child node to the right must contain an integer larger than its parent, and every child node to the left must contain an integer smaller than its parent. As you can see on this slide, we have some examples here of binary trees, ternary trees, and quad trees. If you think you're up to it already, you can try to pause the video now and figure out which is which, but we'll move on from here and I'll switch to a single larger binary tree so we can walk through its structure. So the first thing to notice when looking at a binary search tree is the fact that there's only ever a single node that doesn't have any arrows pointing to it. That node in particular is called the root node. In this case, the root node obviously contains an integer value of 8, specified here at the top, and it has children of integers 3 and 10. Because this is a binary search tree, we can see that all the integers to the left of 8 are smaller, and all the integers to the right of 8 are larger. The standard carries itself all the way down the tree. For example, the node containing integer 3 has only integers smaller than it on the left, so just 1 here, and integers larger than 3 on its right, the 6, 4, and 7 here. In essence, every node in a binary search tree could itself be considered a root if it didn't have any nodes above pointing down to it. So if you plucked off the 6 and kept the 4 and 7, and put this like over here on the left, this itself could just be another binary tree, obviously a little bit smaller. But every node of the binary tree has to live under the same rules as every other node, essentially. Along with the root node, we also have specific naming for the nodes which don't have arrows leaving them, or equally as true, the nodes with no children. These are called the leaf nodes. And obviously, as you can see in the picture, in this binary search tree we have a total of 4 leaf nodes, the 1, 4, 7, and 13. A common metric we can use to get a sense of the size of the tree is its height. The height of the tree starts at 1 when you have a single root, and increases as you add more nodes to the tree. As we can see on the slide, we can easily enumerate the different levels of the tree. So node 8 is at level 1, nodes 3 and 10 are at level 2, etc. We have 3 labels that describe the structural traits of binary search trees. They are full, complete, and balanced. The last of which I've moved on to the next slide because it's somewhat more complex. A full binary search tree is the easiest to identify and is simply one where all leaf nodes are at the same level or depth. In the case of the tree on the left, we can see that every leaf node is at level 4. A complete binary search tree is one where all levels of the tree are filled except possibly the last level, and if the last level isn't filled, all of its nodes are as far to the left as possible. Take note that all full binary search trees are essentially complete, but all complete binary search trees are not necessarily full. A balanced binary search tree is one where no leaf is much farther away from the root than any other leaf. This is a somewhat relative metric, but we can simplify it a bit by enforcing that in a balanced tree, None of the leaves can be more than a single level away from any other leaves. If that is untrue for the tree you're looking at, you can call it unbalanced. Balanced binary search trees are far more efficient when performing search, insertion, and deletion operations, so it's normally favorable to have a balanced tree over an unbalanced. There are actually ways in which to implement a binary search tree that allows it to maintain its balance, even after many insertions and deletions. These are known as self-balancing binary search trees, though these are far more logic intensive, and when we implement the class in Python, we'll try to keep it a bit more simple. We'll get into more detail once we begin coding, but on this slide you can just begin to get an idea of how element insertion is handled by the binary search tree. Here we can see the various complexities associated with the operations you'll often be performing when using a binary search tree, compared to those of an array. If you were asking yourself what's the point of maintaining this more complex data structure system, the answer is that in many cases it allows for faster search, insertion, and deletion operations. The worst case for a binary search tree would essentially be equivalent to a linked list. Imagine the first element you're asked to insert is a 1, then a 2, then a 3, and so on. Eventually you just have a long line of nodes where they always choose to insert at the right child because the new value was larger than the prior. So effectively you've just created yourself a linked list. In this case, we would have big O of n for all operations. You can pause the video here if you'd like to jot some of these down. In a couple seconds we'll move over to a coding editor so we can actually implement this stuff in Python. So now we have our coding editor open, we can implement the two classes we're going to need to make the binary search tree actually function properly. Just on a side note, we're going to be omitting the deletion function just because it's a lot more labor intensive, and there's some other videos on YouTube if you'd like to go check those out. They'll explain all the different internals of the deletion function, because there's a lot of different cases where you could be deleting a node that has one child, you could be deleting a node that has two children, you could be deleting the root node, and so on, and there's just a lot of different cases you have to cover. So just for simplicity, we're going to be omitting that portion. But yeah, so the first thing we're going to be creating is the node class. So we can write class node, create the constructor. We'll be passing in a value that's default set to none, and then we'll be saving that value. And obviously each node has two children, left child and a right child. The left child is a smaller value. The right child is a larger value. So we'll be creating two pointers, one called self.leftChild and one called self.rightChild. Both of these are by default set to none. Obviously, if we're creating a node, we don't necessarily assume that we have other nodes below it already. That'll come into play later when we're setting nodes equal to the children of a current node. And then obviously the second class we're going to be creating is the binary search tree class. Take note that the user is never going to be interacting with this node class. Basically it's going to be, the binary search tree class is going to be a wrapper that handles the management of all of these node classes. And this is a similar idea if you came from the linked list video. Basically in the linked list video we had a node class and then we had a linked list class, and the user only really operated with the linked list class. Same idea here. So we'll call this binary search tree, create the constructor, and in the constructor we're going to be setting a internal variable called root, and then obviously when we first create the binary search tree we don't have any elements inside of it, so I'm just going to be setting the root equal to none. And then the first real function we're going to be implementing is the insert function, which is going to allow you to add elements to the binary search tree. So this is pretty much the most basic of all the functions. So I'll call it insert, pass in a value, and for our entire implementation, if I didn't say it already, we're assuming the values are just integers. So the first thing we're going to be doing inside this function is just checking to see if we can insert this value at the root. If the root doesn't have any value yet, then basically that means that the tree is itself just the root, and we can just insert this value directly at the root. So we'll check and see here if the root is equal to none, just do reset the root equal to a new node with the past value. So right here, this is going to be creating a new instance of the node class, passing in our value as the value here in the constructor, and then the node class will be saving that value internally. And then if that's not the case, if we can't insert at the root, we're going to be calling another private function inside of our binary search tree class with the same name as this function, but just with the underscore signifying that it's essentially a private function. Python doesn't have any actual true private functions, so when a user sees an underscore in front of a function, they should just refrain from calling that function outside of the class. So this is going to be our private insert function, and we're going to be passing in our value and the current node we're looking at, which is the root. And the reason we partition our function into two separate functions is that this private insert function is going to be recursive, and it's easier if we just handle the recursive case in a single function instead of having all of this logic inside of a single insert function that's sometimes recursive and sometimes not recursive. So write out this function, the private version, pass in obviously a value and a current node we're looking at. Recall that the current node we were looking at is the root in the first case. So the first thing we're going to be doing is checking to see if the past value is less than the value at the current node. So if value is less than current node dot value, and then here we're going to be further breaking this case down into two more cases. The first case is that the current node doesn't have a left child, in which case we'll just create a new node and insert the value into that node, and then set the current node's left child equal to that node. So we'll be creating a new left child for the current node. So we can write that as if current node dot left child equals none, current node dot left child equals a new node with the value that we've passed. Otherwise, we're going to be calling the self.insert function again, passing that left child as the current node. Just open this up a little bit more. So if you understand, that's basically where the recursion comes in. So I'll just go over this one more time again. So the first thing we're checking here is if the value is less than the value in the current node. So if the value we want to insert is less than the value in the current node, if the current node doesn't have a left child, then we'll just create a new node and set the left child of the current node equal to that new node. And that new node is going to be storing the value that we want to insert. But if it's the case where the current node does have a left child, then we're going to be calling this recursive function again, passing that current node left child as the current node. So we're going to be entering back into this function, and then current node here is just going to be equal to current node.left child. So this is going to recurse down the left part of the tree. And then there's another outer case here we have to cover. We can just put it into an else, but this is going to be the case where the value is greater than the current node.value. So we're going to want to check and see if the current node doesn't have a right child, in which case we'll just create a new node and set the right child equal to that node. Same idea as up here, except just kind of in the reverse, going down to the right side of the tree. So we'll say if current node dot right child equals none, current node dot right child is equal to new node with the value that we want to insert. Otherwise, we're going to be calling the recursive function again, passing in the value and the current node dot right child as the new current node parameter. And then I'm actually going to make a small change here. This is the code I've been using earlier, but we'll just say if value is greater than current node dot value, because we could have the case where the value is equal to the current node value, and I don't want to have the tree be having multiples of the same integer. It'd be easier if we just pass over instances like that. So let's say, and then else. This is going to be the case where the value equals the current node value. We'll just print out a thing that says value already in tree. So now we can't really test this function out yet because we don't have a way to even view what's inside of the tree currently. So we're going to be creating a print tree function just so we can use that to kind of help us test out the insert function. So we'll call it print tree, passing no parameters. And then the first thing we're going to do is check and see if the root is an actual node. So if self.root is not equal to none, and recall it's set to none by default when you first create the tree, we're going to be calling self.printTree, passing the root as the parameter. And we're going to be partitioning this off into two functions again, one that's recursive and one that's not recursive, similar to our insert function. Just for simplicity and to make the functions a little bit easier to understand. So the private version here is going to be passed a node as the only parameter. And then inside of here we're going to be checking if the node is not equal to none. First thing we're going to be doing is calling print tree, passing the left child as the parameter. Copy this, and then replace this with right child. And then in between these two, we're going to be printing out the value at the current node. So this is effectively going to be an in-order traversal of the tree. And if the whole tree has been structured properly, then this should be in sorted order. So obviously, if you recall, we have integers inside of our binary search tree. Every time we insert something, it's going to be inserted in such a way that when we do an in-order traversal, we'll get the elements popped off in sorted order. That's not necessarily the same if you do a pre-order or post-order traversal, but with an in-order traversal and a binary search tree with simple integer values, we'll always have a sorted order as long as the tree is correct. So we can just print this out. Or I'll make this more simple here. We'll just do string of current node.value. Okay. And now we could just write some helper code to help us test out how the tree is working. We'll use the print tree function to figure out if everything's in sorted order as well. So let's say tree is equal to binary search tree. And then here I'm just going to create a function to allow us to basically fill the tree in with some arbitrary data. So we'll call it fill tree. And then here we'll just call the print tree function to make sure that all these elements are in sorted order. If they are, then we'll know that our tree is functioning properly. So print, I have to call print tree.print tree. Then we'll switch to terminal here and test this out. So python a.py. Alright, sweet. So we can see we have, well, at first we did have some insertion issues, but we have integers in the range of 0 to 1,000, and we have 100 of them printed out in sorted order. And because we're doing an in-order traversal of our tree, if they're in sorted order, then we know that they were actually inserted properly. Okay, so the next function we're going to be implementing is a function that allows us to get a handle on the height of the tree, which is one of the metrics we explained earlier that allows you to kind of get an idea of the size of the actual overall data structure. So we'll call this a height function. So you'll be able to access it by just doing tree.height, and it'll be returning an integer. So height, don't pass any parameters. We're going to also be implementing this one as a partitioned public and private function, where the private function is recursive. So we'll say if the root is not equal to none, return the private version of the function, passing in the root and the integer 0 as the only parameters. Otherwise, just return 0. Because if our root is equal to none, that means our tree obviously has height of 0, because there isn't even an element in the root. So here we can implement the private version of the recursive function. We'll be passing in a current node as the first parameter, and an integer as the second parameter. And then that we're just going to call current height. And then the reason we're passing an integer is that we want to be able to store the height that we've seen on each recursive call. So as we're traversing down the nodes, we might be changing this current node, but if we didn't have a variable either as a parameter or stored as, say, a global variable or an internal variable inside of the class, we wouldn't have a way of knowing the actual height we've traversed over the course of all the recursive calls. So here, the first thing we're going to be doing is checking if the current node is none. We're just going to be returning the current height, because we don't want to increment it at all if the current node we're looking at obviously doesn't have any value in it. So if current node equals none, just simply return current height. And then what we're going to be doing is getting the rest of the height from the left subtree. So starting off from the left child of the current node. And we're going to be doing the same thing on the right subtree. So getting the height from the right child on down to the leaves. And then we're going to be comparing those, seeing which is larger, and then just returning that value. So we'll say left height is equal to a recursive call to height, passing the left child as the value, or as the current node, and then the current height plus 1 as the current height, because we're incrementing the height to allow the value to be tabulated correctly on the next recursive call. And then we'll say right height. Actually, we can just copy and paste this. And then say this has to be replaced with right child. And then here we'll be returning maximum left height and right height. So whichever one of these is larger, the left subtree height or the right subtree height, is going to be the one that's returned from the function in the end. And so if you can think about it on a higher level, we're going to be doing this same comparison at every single node in the tree. So effectively, we should be able to find the part of the tree that has the highest height, or has the highest level its leaves are at. And once we hit a leaf, the current node is just going to be equal to none, in which case that's going to be the base case, and we'll just return the current height. So we can test this out. After printing the tree, we can say print tree height is tree dot height. And because there's 100 elements in here, we really have almost no way of knowing what the height's going to be, other than the fact that it's going to be less than 100, less than or equal to 100. So we can switch over to terminal and run this here. Oh, okay, we got an error. It's line 44. 44. Okay, yeah, so I have to replace that with a period. That was stupid. Okay, so we can see that the tree height is 11, so that's actually pretty good. So effectively, if you're trying to search the tree for a value, which is going to be the next function we'll be implementing, the maximum number of comparisons you need to do is somewhere in the order of 11. So like I was saying, the next function we'll be implementing is a search function. And once again, we'll be splitting this up into a public and private function, the private version being recursive. So we'll write search. We'll be passing in a single value that we want to search the tree for. Here we're going to be doing the same check if the root is not equal to none, we'll be going into the recursive version. And then if it is none, we'll just be returning false to signify that we couldn't find the value in the tree. So if the root is not equal to none, return the private version of the function, passing the value and the root as the only parameters. Otherwise, just return false. And obviously, this search function is going to be returning true if it can find the value in the tree, and false if it can't find the value. You could also change this a little bit so that it's returning the node if it can find a node that contains the value, or return none if it can't find one. But I feel like the true-false is a little bit easier to understand for one, and also it's easier to make use of in your code, because if we're returning the node, you might be tempted to do something on the order of deleting the node, which could substantially cause problems in the tree. So just to kind of keep the actual underlying elements away from the user, we're just going to be returning true and false, and then let the user decide what they want to do with those. So implement the private version here, passing a value, and node, we'll call it current node again. So the first thing we're going to be doing is checking to see if value is equal to the value of the current node. In which case, obviously, we're just going to be returning true. Otherwise, if the value is less than the current node value, and the current node doesn't have a left child, or does have a left child, will be, here, let me just change the size of this a little bit so we can fit it all. Yeah, so if the value is less than the value of the current node, and the current node does have a child, we'll be returning this function recursively, looking at the left child instead of the current node. So search value current node dot left child. Otherwise, if value is greater than the current node value, and the current node has a right child, we'll be doing the same thing as on this line, except we're going to be passing the right child as the next element to inspect in the recursive call. And then if we don't get into any of these cases, or say, for example, we finish this case but still haven't found a node, we are going to be returning false to signify that we couldn't find the value anywhere in the tree. So we can test this out here. Let's just, instead of filling the tree randomly, let's just put in some values that we can know for sure will be in there. So just do tree.insert 0, just copy and paste this. 5. Okay, so we'll print out the tree again, report the tree height, and then we'll print out the results of searching for, let's say 10. Search for 10, which we know will be in the tree. And then we'll print out the results for 30, which we know is not going to be in the tree because we obviously haven't inserted it in any of these function calls. So we can switch over to terminal here and test this out. Okay guys, so we have to make a small change here. I just noticed we were getting the wrong output. We were getting false for both 10 and 30. So the problem is that we weren't actually returning here, so we just have to type in return and return. Because if we enter one of these cases, like value is less than the value of the current node, and we have a left child, we want to return the value that we get from this search. Normally we were just leaving it, and it was just returning none half the time. So returning this value will allow us to report accurately if we actually have the node, a node storing the value, that is. Okay, so if we run this now, save it, and switch to terminal, we should see true and false. Okay, yeah, so now we reported true for there being a 10 in the tree, and false for there being a 30 in the tree, because obviously there is no 30, we'd never inserted one. And since we're going to be skipping the deletion function, I think that's pretty much going to be it for this video. If you guys want me to do another video covering the deletion function, I could definitely started working on that. Just post a comment, let me know. I just think it's probably going to be like another 10 minutes just to explain all the stuff that's inside of that. So I could just kind of update this code with a deletion function if you guys would like that. So be sure to post a comment. Also, if you have any questions, post a comment below. Or if you see any problems with my code, be sure to let me know. But yeah, so I hope you enjoyed the video. If so, make sure to give me a thumbs up and subscribe to the channel if you want to see more coding content and virtual reality, HTC Vive, gaming videos. Other than that, I'll see you in the next video.